feel like, hey, let's just look at some simple bugs, performance problem of loop, so that it's easy to convince the developer. And here's an example. So this is like, there's a array, string array, let's call it, so it's called S. And this loop will go through every element of the string elements. And then it will check, it will call index of, it will check whether any string contains a substring K. And if any string in this array contains such substring, it will set a flag matched to be true. Okay, so for those of you who are familiar, right, with, so this is part of, I forgot this C code, I think it's C code. You may already realize there's a performance problem here, right? So the problem is that really the developer actually, they should break, right? They should add a break after the first time when they find the first string element that contain such a substring. They could have just break. And they forgot to use break. As a result, no matter what, they will always go through every element in this string array. And that is very wasteful. So this turns out, actually, we found more than 100 bugs. And even in very performance highly tuned, like GCC compiler, we actually find such loops that developer forgot to put break. And most of these, because they have very simple patch, most of them are actually accepted by developers. In the next couple of years, then we continue to look at these performance problems. We tried some verification things to see whether we can automatically prove that a performance patch does not change the program semantics. We were also looking at diagnosis problem. Like if I know my software is slow, then how can I quickly know what caused the problem? But that's kind of near the end for me for this kind of generic software's performance problem. And then we started looking at distributed system. And then we see that in distributed system, there are different style of performance problems. And then similarly for web application, for machine learning applications, they each have their own style of performance problems. Okay, so in the next like 30 minutes, I will tell you something that we did about database-backed web application. So first of all, web application, I think we now know is everywhere, and its performance is really important. There are a lot of study, and in general, people found that web users, their patience is about 2 seconds. And if the page does not load within 2 seconds, every 1 extra second will lead to significant, it will cost money, it will make a user uncomfortable. And the bad, slow web page is everywhere. The US government has had several very high profile web applications that perform really bad. And we also did some profiling. So we took 12 most popular web applications, Ruby on Rails web applications on GitHub. And our profiling showed that 20% of these very popular web applications, web pages, take more than 2 seconds to load. And we did this experiment with very medium-sized database. So in real-world deployment, the performance could be much worse. Okay, so then the question is why, right? So why many web applications can take so long, a web page can take so long to load? So let me spend like maybe 3 minutes to tell you how web applications have evolved, just in case some of you maybe are not familiar with web programming. So in old days, it's very simple. For this, like a list of blog titles, you just write a static HTML code. So there's no performance problem, right? Unless your HTML file is big, but even in that case, it doesn't take much time to load. But in modern web application, first of all, people want the content to be dynamically generated. So now there's a application server. It will run some typically object-oriented language programs. And the automatically generated content, like here, these blogs, it actually can be directly used, referred to by its HTML file. And like, for example, here, the HTML, it will just refer to these blogs, this looks like a heap object, right, that is dynamically generated and rendered. And then another aspect is that because modern web applications are hosting more and more data, so very commonly now for large web applications, there are a database engine sitting behind. So the data is now, they're stored in database table. So if we want to retrieve this data, we'll just use a select query. But then from programming's perspective, that's hard, right? For people who are used to writing Python or Ruby on Rails or even Java, it's hard to tell them to embed SQL query inside their code. And so then finally, there's this very popular framework called ORM, Object Relational Mapping. So what it does is, and this is implemented in Java, Python, Ruby on Rails. So now certain class will automatically be translated into database table. All the class property, they will automatically become table column. And inside your object-oriented program, there's certain ORM API, or sometimes even look like heap access, like this blog.org. It will be automatically translated to SQL query. So that's how today's application works. It looks all fine, right? Now the web developers, they can quickly write a lot of web pages. They can be designed to have very beautiful interface and manage a lot of data. But the problem is there are a lot of performance complaints. And why? So there are mainly two problems, which are the two problems that I will repeatedly refer to later on when I talk about our technique. The first problem is that the application developer, now they do not have much sense about what queries are issued at runtime, right? Because they write object-oriented code. And it's just like, for example, say in this case, right? They may write blog.org and again and again. And then to them, they may feel like it looks fine, right? I'm just doing heap access. And they don't realize that these are actually translated to many, each of these will be translated into a SQL query, and it's very expensive. And not only that developer don't know them, compiler are also not aware of this. So our compiler that does optimization, they treat all these ORM APIs as black box. So you can imagine there could be a lot of inefficiency. And also, there's also not much database engine can do. The database engine, it can generate efficient query plan for each query, but it cannot do more kind of global optimization because it's not aware of application semantics. And this can lead to a lot of slowdowns, and fundamentally, this is a problem of lack of cross-stack optimization. This is the first challenge. The second performance challenge is related to interface design. So in the past, right, people who write HTML, they know these are the features that I display, and I know what exact data is being displayed. But now, like, because of there are so many, their application layer and database layer all the way. So people who write this HTML, right, it only know that, okay, I'm going to display the number of comments. And it's really difficult for them to realize how complicated it may be to generate this number that they want to display. So like, for example, in this case, here it generates all, this application generate all the comments related to these blogs that are undeleted yet. And this turns out it takes a join query to generate. And it's really expensive. And in our profiling, with a very small database, it takes more than 1 second to just generate this a kind of anecdotal number of comments, right? And actually, a similar problem happens in real application. And once developer realize that it takes so much time, they actually just simply deleted this tag from their web page. So that's a second challenge. We feel like there's really a lack of user interface optimization support. And there's just basically no support for web designer to design performance-friendly web interface. Okay, so so that's the problem we were looking at. So next, I will tell you first how we started the whole thing. How we did a taxonomy, we did a study about all the performance problem in web application, and this study led us to realize these two challenges that I just told you. And then we basically work on the problem at each layer, right? For the at the interface layer, we try to help developer to design performance-friendly interface. We build some program analysis tool to try to detect inefficient use of ORM API. And we also did something at the database layer to try to leverage application semantics to optimize database design. Yeah, so this series of work, it got a lot of actually attention in open source community because apparently web developers actually, they have struggled at this performance for a while. And we did find thousands of this type of performance problems in just these 12 popular open source application. Okay, so first let me quickly go through this empirical study that we did. When we started this project, we did a Google search, and we found there are many complaints. And there's also a lot of blogs telling you here's some tricks about how to write well-performing web application. And we also saw actually about the time that we started, we saw their researchers, they are already looking at these problems. But still the work is great, but we feel like we still don't know what are all the problems, right? Except for the problem that are already tackled by some of these papers. So because of that, we decided that we want to do a study ourselves to first understand what are the problems out there, what are the most common types of problem, how severe are these problems, and how complicated are the fix. As I said, so we decided to look at Ruby on Rails application, which is the most popular language people use for web application. We go to GitHub and we look at for the 6 most important application category. For each category, we pick the we take the 2 most popular, like the one that have the most stars on GitHub. And then we checked their issue system, bug report system, and we collect more than 200 problems, including about 140 of them that are already reported and already fixed by developer. And we also look at 64 problems in the latest version of software, which found by our manual profiling. And in terms of categorization, so our paper has more detailed anti-patterns, but at a high level, we did see that the problems go across all these 3 layers, exactly like what I mentioned. About half of them is because developer, they're not aware of the existence of SQL queries, so they write some inefficient code. About a quarter of them is because of interface design, another quarter of them is about database. And how severe? So we did a profiling for those 64 issues that we found ourselves through profiling. And we found out that actually more than 60% of these 64 problems, each of the problem lead to more than 2 times slowdown for the end-to-end page loading time. So it's quite severe. And particularly among this problem at this 3 layer, the interface problem actually has the biggest impact to the performance degradation. And finally, we found out that more than 80%, most cases, the fix actually are pretty simple. So this gave us the hope that, hey, maybe we can potentially automatically synthesize the patch and so on. Okay, so yeah, so this work, it turns out it was very well received, and it was featured on Morning Paper, and a lot of developers like it. So next, given the time, I would just mainly tell you what we did to help interface design. And if I have time, I will just briefly go through how we automatically detect those inefficient API usage. Okay, so for interface, as I said, we found this to be interesting, first of all, because it leads to significant performance slowdown. And just to give you an example, what do I mean by interface design problem? So I will show you 2 web pages. Actually, we did exactly this type of user study through Amazon Mechanic Tag. In our user study, we actually show people that we tell people that there will be 2 web pages. You can click them one by one. And after you see both of them, please tell us which web page you prefer. So I will just show you these 2 pages side by side. So pay attention to how similar or different these 2 pages are. Okay, so I'm going to load both pages. Okay, so these, the left-hand side and the right-hand side, right? So you can imagine most developer. So by the way, so there's a black circle. That's what we just add for this presentation so that you can know more clearly what's the difference. Okay, so most people, right, they prefer page 2 because you can see the page loading time difference is obvious. So the trick here, what is different is that the only difference is the page 2, they let this particular region of the web page to be loaded asynchronously. The reason is just this very tiny region, right? If you look at the whole web page contains a lot of information, but just these 2 numbers, it takes the majority of the time to load. So if we just asynchronously load this small part of the web page, it won't affect users' viewing experience, and it can load the web page much faster. Okay, so this is a type of interface design problem. And it is as we said, it's a big problem because this is completely out of the scope of traditional code optimization, right? So for traditional compiler optimization, it's important not to change the program output, right? But what we want to do here is exactly opposite. And because we need to change the output, it's hard to do this completely automatically, right, behind the developer, because now we have to face a trade-off between the interface usability and the performance, right? So it's like a very silly tool to say, hey, let me just remove all the content, right? And then the web page will load very quickly, but clearly this does not work. So that's the first, it's actually a research challenge that we need to face. The second challenge is that you can imagine, since I told you, right, these 3 layers of web application, if we want to do something to the interface, it will end up change the application code, and it will also change the queries that get sent to the database. So we will really need a cross-stack analysis to enable this. Okay, so just to tell you, first, let me just quickly tell you what at the end, what do we get? So we ended up design actually a kind of like a development environment, because we believe this type of optimization has to involve developer, right, in this cycle to decide. So instead, we offer an environment that when the developer, after they finish writing their web application and when they want to test it, we will do a cost estimation at a HTML tag level. And this cost will involve our estimation about not just the HTML itself, right, clearly. We will estimate how much computation and data processing time will be needed to in order to render every tag on this HTML page. And then we'll visualize this through a heat map. And then we offer different options for interface refactoring. And we automatically do this refactoring to developers. So developer can just simply, so in our heat map, right, the darker, the more expensive. So developer could say, hey, this tag is the most expensive tag on my web page. What can I do? If he or she right click, and we will show that. You could try, right? These are different things you can do for refactoring. And if the developer say, hey, I want to try approximation, and then our tool will automatically rewrite, the HTML and everything, and we will show a updated web page to the developer. And then you can see now the cost goes down. And the developer, if they're not happy, they can go back and they can basically navigate to see what are other things they can do for other part of the web page. For example, here, if you try pagination, right? Similarly, will automatically generate a paginated version of the page. Okay, so that's what our tool offered. And given the time limit, I will just very quickly tell you what exactly did we do to enable this interface refactoring. Particularly, I will tell you what type of refactoring we do, when, and how we do it. So what type of refactoring, right? As we said, some changes are just not meaningful. So we actually checked different web applications design, and we categorized refactoring to be two types. One type is we display the same content, but in slightly different format. And this include like asynchronous loading and like a pagination, right? So ultimately it's the same content. It's just that it will be loaded in a different form. Another way is sometimes we will just display, we call it simplified content. One is remove one tag. Right, you cannot remove the whole content, but maybe you can just remove one particular expensive tag. Another way is approximation, which I showed you. Like instead of showing how many comments you have, maybe I just show you you have more than how many comments. So now these in our paper, these are the particular 4 types of refactoring that we focus on. Now the challenge is how can our program analysis tool automatically judge when to conduct certain type of refactoring. And I want to emphasize that, again, this is not the traditional type of optimization. So this refactoring decision sometimes is actually subjective, right? As an experienced developer, they would look at this and they would just have a gut feeling, right? They would feel like, hey, here you have a long list of items to display. As a result, maybe we can try pagination. So what we need to do is we need to turn this kind of subjective decision-making process into something that program analysis can automate. And I will just quickly go through this pagination example, right, to tell you what kind of program analysis we do. And I will go through the code together with you. I will go through the code behind this web page and give you a sense about, first of all, if I want to do manually code checking, how can I make this decision about doing pagination? And then I will tell you how we can automate that manual code checking. Okay, so this HTML, so this actually corresponds to this part of this HTML code. So you can see there's some HTML tag here indicating the format of the output, and this percentage sign. So in Ruby on Rails, this indicates that they will embed Ruby code. And then you can see the embedded Ruby code, particularly is referred to variable blocks. And these blocks is actually generated in this controller. So this is basically it's a function. This function is called whenever the index HTML file is loaded. And okay, so now going back, right? So how we can translate this kind of feeding, right? Long list of items on web page into some features inside our code. So first of all, this list of items on web page, right? So you can see this actually can be mapped to it's kind of like if I see a loop, right? Inside HTML. And in each iteration of the loop, I'm displaying some HTML tag. Okay, so this by looking for these features, right, like loop, HTML tag inside HTML file, that can give us a sense that, oh, here I'm displaying a list of things. But that's not all, right? If I'm just displaying a finite set of things on the web page, it may not be worthwhile to do pagination. So another thing is, right, as a human, we typically would say, hey, if you have a long list, then I want to split it to pages to load, right? So what can represent the concept in long? So in this particular example, you can see this block, right? So this loop, the number of iterations that this loop will have is determined by the number of records that will be returned by the select query. Okay, so now if I'm manually checking this code, I can see that because this is a select star, so we can call it a scaling query, right? So this query result, its size is unbounded. The number of records returned, it will linearly increase pretty much, right, with the database table size. So that's how, like, if I'm manually checking this code, I can say, hey, here is a scenario that pagination is needed. And if we want to automate, right, this code checking, the first thing is we will need to know what application code is used to generate which HTML tag, right? And then secondly, if I know that, then I would want to know, right, whether there's any scaling query behind the application code that is used to generate HTML tag. So if we know both, right, then we can automatically decide refactoring. And then just very quickly, clearly not every tag, right, is suitable for refactoring. And indeed, like if you look at this comment, like there's a tag showing how many comment, right? First of all, you can see there's no loop involved, right? Secondly, the state application statement used to generate it, it is backed by a select count. And select count is not a scaling query. No matter how big the application is, it will only return one number, right? So basically this just tells you that we can indeed, by analyzing code, right, we can do some interface decision. Okay, and so they're similar basically to, for other type of refactoring, the checking process, it is similar. Like for example, for asynchronous load, we just want to make sure that you better asynchronous load the most expensive tag on your web page. Okay, and then to do that, similarly, we have to figure out what application is used to generate application statement, right? And also which query is used to generate a tag. And we need to do some complexity analysis, right? Like in this case, I can tell you the comment, it takes n cubic complexity to generate. And that's why it will be the target for asynchronous loading. And there are other things behind this, so I will skip all these. So how do we automate all these, right? So how do we know which application code is used to generate which HTML tag? Okay, so if there's no HTML, if there's no cross layer here, then the question about what statement is used to generate which data, this is just a very classic data dependency analysis, right? And indeed, like if I show only this is a Ruby code, right? Then the Ruby compiler actually already, their existing compiler framework that can give us this data dependency, program dependency graph that allow us to know, right, what statement is used to generate which variable. The challenge here is that now we are talking about there's some variable referred in HTML. So we need to create this connection between the Ruby code and the HTML. So what we do is we extend the HTML parser. We first extract all the Ruby code from HTML, and we also keep a note about, because HTML parser will also tell us what tag this Ruby variable is used. And then we extend the Ruby compiler. The Ruby compiler will check, because all this HTML, the connection is this render statement. So I will skip the detail, but at high level, we will analyze the Ruby code, and then we will inline this render with the corresponding Ruby variable used in certain HTML tag. So there are of course, a lot of effort work behind this, but at the end, we will be able to get a program dependency graph that include not only Ruby code, but also HTML information. And this will allow us to easily check this graph and know that for each HTML tag, what are the application effort behind it. And then we also further extend the Ruby compiler so that it can recognize those statements that will be translated to SQL query. And we also extended so that it can recognize what a skilled inquiry, what is not, and also we also extended to do some query complexity analysis. So basically, it's all these, right? So this is this has a lot of work behind this, but at the end of the day, we have this compiler infrastructure that allow us to do this cross-layer analysis, and with that, we'll be able to do all these refactoring, and we can in fact automatically generate patches. Some of this pagination patch is simple, and here is a patch for asynchronous loading. This is a little bit complicated, but overall, this is all automated because we have this cross-layer program analysis. So overall, we find actually in the latest version of this 12 popular application, we find there are many optimization opportunity. They lead to many times of end-to-end page loading improvement. We did a user study. I will skip it here. Overall, the user, most cases, they like the new page significantly more than old page. Okay, so yeah, so this is work that won the SIGSOFT Distinguished Paper Award. Now let me just use like a couple of minutes to quickly tell you how do we handle this inefficiency in application. Okay, so these are the most common type of performance problem in web application, although not all of them lead to as severe a slowdown as your interface design problem. They come with various types. Like one example is in Ruby, there are two APIs, presence and exist. They will both tell you, they will both return true or false that tell you whether a container contain any element or not. And they have exactly the same semantics, right? The question is then why do I have two different API? So it turns out if that container is returned from database, and we just again use some very medium-sized database, and you can see there's thousands of times performance difference. The reason is it will be translated into different SQL queries. The first one, it will select all the records from a table and then check whether this number of records is a positive number or it's zero, right? Which is quite silly. And the second, it will do select one. So basically it will, once it finds the first record that satisfies a condition, it will return. And so for example, in blog, right, actually really in application, you can imagine, right, this name is so similar, a lot of developers would use them wrong, and that will lead to huge slowdowns. And another example here is like, this is a loop. The code will go through all the blogs, and then it will check whether any blog's title is in a block list. And then it will delete, it will remove those blogs from the display list. If you just look at this, there's nothing wrong, right? Except that remember that I mentioned to you, so this block list.all, it actually is a select query. So essentially, this select query will be repeatedly issued in every iteration of the loop, and they always return the same result, right, inside this loop. So this is actually, if you're familiar with right, I'm sure, so you know that this is actually a loop invariant motion. You can just compute this, issue this query once at the beginning, right? But because developers, they didn't realize this is a SQL query behind this, so they missed this. And again, a lot of slowdown. And there are other cases that your application, they load data, they do not use it, and then they load it again and again. And all these different problems, right, they exist because our object-oriented program compiler, they're not aware of ORM, and they treat this as black box. And if we want to, right, the challenge is we initially thought about, hey, maybe we should write a checker for each API misuse, each anti-pattern. But that would be like too many checkers to write. So fortunately, we found out that we found out that actually a lot of these problems, they correspond to traditional compiler optimization, like strength reduction, loop invariant motion, and so on. As long as we have the compiler that do not treat ORM as a black box. And that's exactly, right, that I already told you that we have a compiler infrastructure that does exactly this. So I will skip all these, but basically the idea is that now we have extended the compiler, right? So compiler knows which statement is a query, and whether it's a read or write, and what database field it will access. So this new compiler that we extended knows all this information. And then you can just apply the traditional compiler optimization, it will find and fix all the problems. Okay, so at the end, we actually found thousands of bugs in just the latest version of these 12 applications. And these two have been downloaded many times. Okay, so as a conclusion, I quickly went through these works. I think one kind of takeaway I got is that really modern software just has too many layers and has too many abstractions inserted. So how to do cross-stack optimization is really crucial. And the second thing is this user interface optimization. I found out that it's actually very important. No matter how good, right, as performance engineer can do, if the interface designer is unaware of the performance trade-off, those problems cannot be solved by just back-end optimization. And I will leave my talk here. So it has been a fun journey to looking at the performance problem in various different types of software systems. Thanks very much.
So thank you very much. It was a very interesting presentation. So are there any questions from the floor? Can you please raise your hand and then I will assign the mic to you.
Okay, let me stop sharing so we can see each other.
Okay, so while other people are maybe writing down their questions, I have a question for you. So it seems that a lot of these changes are on the server side of the applications. But also a very important aspect is the client side, right? So, and if you work with web applications, then you know that almost everything that you do can look very different across browsers and can render very differently. It can be much slower, much faster. So is this something that you take into account as well, and how do you deal with this?
Yeah, that's a very good question. So actually, our work exactly. So in our work, we're only looking at server, and I know there are people looking at particularly like some application, a lot of applications, they may use JavaScript client side, and that would completely change the performance. So the reason we did some profiling, and we saw that for these 12 applications that we are looking at, about 70% of the time is spent at the backend. I think it's probably because these are applications, they're heavily using database, right? So that's why the database part spend most of the time. But even in these applications, I have to admit, right now, because so some of them, they still use, it's a mix, right? So there are some front-end processing. And actually that's sometimes, occasionally, that can cause our program analysis to have false positives or false negatives because we're not analyzing the front-end code. So yeah, so overall, I would just say, I think, and including the cost estimation thing, we noticed that actually browsers, I think Chrome and Firefox both, they actually already have some plug-in that they will show you the complexity considering the client-side script that you are writing. It will tell you how much client-side complexity you have, but those browser tools, they cannot cover the backend. So that's also why we feel like, hey, let's do something about the backend, which has not been covered and is important for a large type of application. But you are right? So to completely solve the problem, the front end also has to be considered.
Okay. So I see a question from the floor from Alberto. Can you please ask your question?
Hi, thank you very much for a very nice presentation.
Thank you
very much. And I see that the most difficult performance problem in my web applications in my phone is not related to the implementation of the developer, but the environmental conditions, especially the ads that get loaded. Sometimes the page is stopped there for 1 minute while the ad is loaded and it's full of animation and all kinds of things, right? So how you deal with the end-to-end customer experience, right? Where there are many other things that happen that you're not aware of.
Yeah, that's a good question. So we are, I have to say, yeah, this ad thing is an interesting thing. We have not in our work, because we focus on these open source applications. So in this platform, we have not seen the ad thing. But I can imagine if, for example, right, like if the ad, the advertisement is explicitly part of the web application, I think potentially some of the design, for example, I know on some website, the ad is loaded asynchronously, right? And I always have much better user experience. So I think some of the kind of design principle, it can apply even to this ad. But I think you mentioned like phone. I do think phone is very different from web application, because for web application, right, it's kind of like the web, right? The web kind of like it's a bigger area, right? Bigger space than our phone. So for web application, right, there is this issue about there are many tags, right? And how do I arrange these tags? How do I, this interface design? I think for phone, I agree. I think it's a very different thing, right? It's like on my web page, when the ad is loaded, it can just be a corner of my web page, right? So it does not hurt the overall performance. But for phone, right, when the ad is loaded, you don't see anything else. So I think that actually, I think it's exciting, it's an interesting research direction to look at how things are for phone. We did when we talked with some company. They actually mentioned to us saying that this database issue is also a problem for their phone app, because a lot of phone app, it's similar, like people who design a app on the smartphone, they just use some library API that allows them to use the security library, right? To use a database library. And there's a similar performance problem that they use this API in a performance unconscious way. But then I think there's also special thing challenge related to app. Yeah, I think that's probably a whole new research direction to look at.
Okay, thank you. We have time for one more question. So Andre, can you please ask your question?
Are you actually counting the database queries that are generated, looking at the reduction in database queries so that you can see what the impact on the back end is going to be? That way you could help make the business case for what you're doing in case you encounter resistance, because there's an inherent cost at the back, and by reducing these query rates, you might be improving the response time for everybody.
Yeah, exactly. That's a very good point. Indeed. So actually, when we do this interface change, there are cases that actually sometimes because of the page loading time actually does not change that much, or it change a bit, like for maybe it is reduced from say 3 seconds to 2.5 seconds. And the end user, sometimes they don't see the difference. But exactly like you said, actually we mentioned this in the paper that even if the end user doesn't see much difference, we think that's still helpful, because exactly like you said, because we have reduced the query, right? So it's a beneficial thing for the whole ecosystem, because now the
monetarily
database,
as well, if you're in the cloud.
Yes, exactly. Yeah, indeed. Yes, absolutely right.
Thank you.
Okay, then I propose that we finish the keynote here and then we go to the break. So I would like again to thank Professor Shan Lu. So thank you very much for being here. It was a very interesting keynote.
Thanks very much.
So we will now have a break of 5 minutes, and then we'll continue with the next session. So see you everybody in 5 minutes.